synthesis of alumina, which is a drying agent, very important industrially. This is the balanced equation. All right. All I give you is that equation, and I ask you the following question. At what temperature do I need to have this reaction going in order for it to occur spontaneously? What am I going to do? The question is, what temperature is required for this reaction to occur spontaneously? Now, what we're going to do is we're going to employ the definition of Gibbs-Helmholtz energy, which we know delta G equals delta H minus T delta S. And we're going to simply say, okay, in order for the reaction to occur spontaneously, what must happen? Correct. So, it follows that delta H minus T delta S must be less than 0. That's what we're going to solve for. Now, how are we going to solve for delta H? Well, what we're talking about here is the free energy change associated with the reaction. So how are we going to determine delta H of the reaction? Well, we're going to use this table. The delta H of the reaction is going to be the sum of the enthalpies of formation of products minus the sum of the enthalpies of formation of reactants. So let's have a look. What are the products? The products are simply alumina, Al2O3. Do we have alumina on the table? Yes, we do. Alumina is right over there. Al2O3. Do you all see that? Its enthalpy of formation is minus 1675.7. Now, in this balanced reaction equation, I have 2 there. So I have to multiply it, because that's the enthalpy of formation per mole. So basically, it's going to be 2 times minus 1675.7. That's in fact the only product I have, right? And that is the sum of the molar enthalpy of products. Does everyone agree? It's taken because of this. Don't forget this, guys. Don't forget this. This table is expressed in per moles. I don't have, according to the balanced equation, 1 mole, I have 2 moles. So that's why it's 2 times that. Now, we can, without even looking at the table, know, so that's the sum of the enthalpy of products, molar enthalpy. What is the sum of the molar enthalpy of the reactants going to be? No. Look at the table. Aluminium, solid, oxygen, gas. 0, 0, Y 0. In their standard state, exactly. So it's going to be this minus 0. Now that's not always the case, right? Sometimes you have reactions where you have products that are not in their standard state, so watch out. Then you have to consult the table. But it's the sum of the enthalpy of products minus the sum of the enthalpy of formation of reactants. And now we get a value of 51. Doesn't matter. It's a rounding error. Alright, that's what I have.
So imagine if they weren't in their standard states, would you guys
If they weren't in this, of course. Because this table is in kilojoules per mole. So if this was, for example, aluminium gas, then you'd have to take the enthalpy of formation into consideration. Alright, so that's the enthalpy. So what is the conclusion? The conclusion is that the delta H of the reaction is what? going to determine the entropy change of the reaction in a very similar way. You take the sum of the entropy of the products minus the sum of the entropy of the reactants to get the overall entropy change. We go to our table and we look at alumina, and we see that the entropy per mole is 50.9. So what's the sum of the entropy of the products going to be? 2 times 50.9. Minus what? Minus the entropy of oxygen and the entropy of aluminium. The entropy of oxygen gas is 205 and what? Exactly, we multiply it by 3. So it's very good. So it's going to be 3 times 205 plus, what is the entropy of aluminium? 28.3. But we've got 4 of them, so it's 4 times 28.3. And you get a grand total of minus 624.4 joules, be careful here, joules per mole Kelvin. Those are the units of entropy. So it's actually very simple. You take the value straight from the table, you look at the balanced equation, you sum the enthalpies of the products minus the enthalpies of the reactants, you get the entropy change of the reaction. You sum the entropies of the products, you subtract the enthalpies of the reactants, you get the entropy change of the reaction, and then what do? What do then? You substitute the values in and solve for T. Alright? So delta H, let's do that. If you substitute the values in, you're going to get the following. You're going to get the following. You're going to substitute these values in here into the Gibbs-Helmholtz equation, and you're going to get minus 3351.4 kilojoules per mole, right? Kilojoules per mole. Minus T, delta S is 624 joules per mole. So we have to convert that to kilojoules, right? Which is what? No, 0.624 kilojoules, because that's joules to kilojoules we divide by 1,000. And if you basically then, remember this is all less than 0, if you solve for T, what you get out at the end of it all is 5,350.3 Kelvin. So in other words, for this reaction to proceed spontaneously, you would have to do it at just over 5,000 degrees, which is the minimum temperature where this reaction would occur spontaneously. Basically, what you can also think of doing is just set this equal to 0, and yeah. That's the temperature required. In fact, formally speaking, that's the temperature where the reaction would be at equilibrium. But I mean, 1 degree higher than that and you'd have the reaction spontaneously. So it's very simple. You basically take the reaction, you balance it. Yes? At equilibrium, but, because remember, if delta G equals 0, it's at equilibrium. But if delta G is negative, in other words, just 1 degree less than that, it wouldn't be spontaneous. So the answer is any temperature lower than that would yield a spontaneous reaction, essentially. It gives you the numerical answer of the equilibrium, of the reaction being at equilibrium, but of course we know just less than that it would start being spontaneous. So that's the way to think about it. And the other thing is, it's actually very simple. You just plug in the values. Where? That's 2 times 50.9, and that's 3 times 205, plus 4 times 283. You had a question.
Yeah, how do the minuses, I don't know if it's like, maybe I'm lying, but I just want to see how.
Because that's minus. That's minus. A minus and a minus is a plus. And it's algebra. This comes down to simple algebra and working with inequalities. But do you understand why this is important? Why is this important? If you're an industrialist, if you're a chemical engineer, and you want to synthesize something, you want to know what temperature is required for that reaction to proceed thermodynamically. It doesn't say anything about the speed of the reaction. For that, you have to consult somebody that's working in catalysis and kinetics. But just to get the reaction to go, you have to fiddle around with the temperature so that you reach a temperature where delta G is negative and the reaction proceeds spontaneously. This is of enormous importance. And if you become a chemical engineer, this is chemical engineering 101, right? The first thing chemical engineers learn about is the Gibbs-Helmholtz energy, because it dictates the condition whereby a reaction is spontaneous. Now we could play the game the other way around. I could give you a reaction and say, is this reaction spontaneous at room temperature? What would you do? Well, you would do the same thing. You would just then plug in for temperature 298 Kelvin, because remember in thermodynamics we work in Kelvin. That when we were doing those calculations with Q earlier in the lecture, I used degrees centigrade. But the thing is, that's okay, because it's a change in temperature, so the units don't really matter. But in thermodynamics and in chemistry, if you ever see temperature, use Kelvin. In fact, what I should have done earlier when we were looking at that example with brass and heating up water is do it in terms of Kelvin. But it doesn't really matter there, because delta T is a delta T, whether it's Kelvin or Celsius in material. But if I were to ask you if a reaction is spontaneous at room temperature, you would plug in this value, and that's basically what you would do. And this was last year's exam question, this one. And only a couple of people in the class got it right, for the following reasons. They always forget to multiply by the stoichiometric coefficient. That's one mistake, students. Second mistake, they don't balance the equation properly, then everything is wrong. Third mistake, they forget to multiply the entropy values of products and reactants by the stoichiometric coefficients. Fourth mistake, they forget that the zero values for the enthalpy of formation only applies to enthalpy, and they think that the entropy of elements is zero. It's not zero. Of course, we see that everything has a positive value for entropy, even if it's a solid, which makes sense, right? Because we're not working at absolute zero, and so on. Now, I want us actually to do another example together if we have some time. We do have some time, in fact. No, we don't. Maybe we should do an example in the tutorial, because this is an absolute must. All this thermodynamics mumbo-jumbo that we were talking about earlier, you know, these philosophical things, is not that important. What is important is that you can do equations involving the Gibbs-Helmholtz equation. That's a hint. And that's of paramount importance. And so I want you to understand this equation very well and be able to apply it. This is very important. Well, I'm not going to give you the Gibbs free energy equation, because this is something you have to really just memorize. It's one of those equations that are so important that somebody that has done chemistry at this level should just know it, as well as delta G equals negative NFE. I expect you to know those two equations.
But the constants will be given.
Of course. Definitely. And the other thing I expect you to know, well, I expect you to know those two equations. And I don't expect you to memorize the Nernst equation. But this has been our last lecture.